Hey guys, we're going to talk about simple pendulums today, and I'm going to derive the equation for the period from this. We've seen this previously because it's pretty common. These show up in conservation of energy problems where you do work on the bob, you displace it a certain distance, you release it, and that work that you did was potential energy, gets turned into kinetic energy, and you can find out how fast it's going. So for this, the mass provides all of the mass of our system. The cord doesn't stretch. The cord is also massless. All right, so here is a picture of what this looks like. And we have theta, we have L. I'm going to draw in a couple other things for us. So I'm going to call this X. And the motion of the pendulum back and forth is going to be sinusoidal. So I can represent the motion of this back and forth as X equals A cosine omega t. So that's going to be able for me to represent the velocity as the derivative of this with respect to time, which is going to be minus omega A sine omega t, and then my acceleration is going to be my second derivative with respect to time. And this is going to be minus omega squared A cosine omega t. All right, so we need to make a couple of assumptions for this. This formula is only going to work for small angles. And I'm going to say theta that is less than 10 degrees. And so in these assumptions, our first one is going to be that sine of theta is almost exactly theta for small angles. And we have a slide. I'll just go forward to show you in the notes where they show that. But if you can see over here, they show you what theta is and what sine of theta is. So for 1 degree, the difference is 0.005%. For 5 degrees, it's 0.1%. For 10 degrees, it's 0.5%. For 15 degrees, it's 1.1%. So even up to 30 degrees, there's still the difference is only 4.5%. And my second assumption is that my cosine of theta is essentially going to be 1. So it's very close to being 1. So why is this important? We'll see shortly. And that's going to mean that we're only looking at back and forth and it barely moves up or down. All right, so first thing is I'm going to say that there's forces acting on this bob. And the forces acting on this bob is mg going this way and t going that way. And so t is at an angle. I know when I have things at angles, I want to get rid of them. And I'm going to have a component that's going to be t sine of theta and a component that's going to be t cosine theta. In the y direction, I'm saying it's not accelerating. It's barely moving up or down. Its motion is all in the x direction. And so I can say that my force up, which is t cosine of theta, is equal to mg, or that t is equal to mg, because I'm saying that cosine of theta is essentially 1 for small angles. In the x direction, we are accelerating. And our acceleration is going to be given by t sine of theta. So I know that t sine of theta is equal to ma. Now I also know that sine of theta is essentially theta. If I look at my triangle here, I can see that sine of theta is going to be my opposite side over my hypotenuse. And so theta is essentially going to be my opposite side over hypotenuse. So for my negative t theta is equal to ma, I'm going to plug in x over L for theta. So I'm going to have negative t x over L is equal to ma. And then I also know that t equals mg. So I'm going to have negative mg x over L is equal to ma. And I'm going to cancel out an m. And I'm going to substitute in for x and a, my a cosine omega t and my negative omega squared a cosine omega t. So I'm going to have negative g over L a cosine omega t is equal to negative omega squared a cosine omega t. And look at that, I can get rid of both the negative and the a cosine omega t. So I need a little bit more room. I'm going to scroll down. So what we have is that g over L is omega squared. Now this isn't angular velocity. This is angular frequency. And it's confusing because in the previous chapter, it was angular velocity. But this angular frequency is 2 pi divided by the period. So I'm going to plug this in for omega. And that's going to give me that g over L is equal to 4 pi squared over t squared. I'm going to move this around. And so I'm going to get that t squared is L over g times 4 pi squared. I'm going to square root both sides. And we get that the period of a pendulum for small angles, because I made those small angle assumptions, is 2 pi times the square root of L over g. So how is this like the mass spring equation? And both of these are on your equation sheet, but I just wanted you to see that they don't come from nowhere. We got them from somewhere. So how are these the same? And neither one of them does displacement matter. How are they different? Mass doesn't affect pendulums. So our mass canceled out. So that's going to mean that whether you have an elephant on the end of a string or a 1 kilogram mass, if they have the same length from the fixed point down to the center mass of the bob, they're going to have the same period. How else are they different? Gravity affects pendulums. So if we take our pendulum into an elevator that's accelerating, if we take our pendulum to the moon, we're going to get different periods. For our mass spring system, I can be accelerating in an elevator. I can be on the moon. I can be on Jupiter. I'm going to get the same period. So that's how they're different. And again, this only works for small angles, which we'll see in the PhET, that you can change the angle and you can see that they differ just barely because the displacement shouldn't matter.